To conclude our lesson on singly linked lists, I would like to do two things. Number one, I would like to assign two extra exercises to you, which will be quite important to really visualize and implement and test. I'll do the visualization part together with you, but you should really try to implement the code and also to test it. And the second thing I would like to do is to summarize the performance between arrays versus singly linked lists by using a table. That's definitely worth doing together. All right, let's do the first thing first. So let's now consider two linked list operations where a reference node is given as an input parameter. So that means we don't necessarily have to really start from the head reference of the singly linked list. Sometimes you might just be given some node to really begin with. Maybe the node is somewhere in the middle of the of some maybe singly linked list maybe. So that can really change the performance about a story. Well, let's take a look. Okay. So we got two methods over here to think about. So one is called insert after, the other one is called insert before. And the colors I'm using here somehow suggest which one is actually cheaper than the other. If you know my color convention, you will see. But let's now take a look. So insert, both methods over here, it's a mutator method. Okay, and it takes two parameters. One is certainly some reference node. So this is what I call a reference node. Okay, let's now highlight it very quickly. Node n over here, and also node n over here is simply some reference node, and it will be quite important for you to really picture yourself how to really contextualize this reference node. Okay, let's take a look. So reference node, and because it's simply just a node, so you can think about the node, for example, n over here, and maybe just a reference of certain nodes, and the node here might be in somewhere in the middle of some maybe singly linked list over here, somewhere in the middle. It could be the beginning, could be the middle, or could be the end. That's not our concern. All our concern about is that we actually got a reference of this particular node. That's what we should really remember. Okay, let me just call it that, and just make sure we know this is a reference node that we're dealing with. And similarly, we're dealing with this reference node over here. Okay. Just don't get confused that you don't think that this node over here appears maybe after this particular node over here. That's not what I meant, right? You can see it's just somewhere in the middle of the list, somewhere in the middle of the list, like that. Okay, let's talk about each one about like a one by one. In the case of insert after, what we want to do is really to create certain node storing this element e. Maybe e is simply pointing to some string objects. And then the new node is going to be inserted after this particular node over here, right? Let's think about what's going to happen over here, right? For the first one, visually speaking, we're definitely going to first of all create that new node. Let's say we're going to create this new node over here, okay? And the element part and also the next part, right? The element part is actually going to point to wherever e is pointing to set it, right? And now we want to say this new node should be inserted after the reference node over here. So that means reference node, rather than pointing to what it used to be pointing to as the next node, is going to be pointing to this node instead. Not only that, you want to make sure the next of the new node is now going to point to wherever that used to be the next of n over here. So in that case, we're going to, let me just draw that, right? I got some hints written in the slides for you to implement. So what's going to happen is we want to make sure, rather than pointing to over here, from n.next, it's now going to point to this particular new node over here. And the new node's next is going to point to wherever n.next used to be. So that'll be the chain of nodes. So after this n, we go to this new node. After that new node, we actually go back to the whatever the next of n is. And of course, the dot 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 over here tells you that it could be a single node or it could be just a chain of nodes after that. So that's why the insert after here, you should really understand what the reference node, the role of that. In the context, it's simply just somewhere in the middle, maybe of some chain of nodes, and you're just trying to insert somewhere in between over here. All right. All right. So that's about the insert after, and this part here seems like it will just be big O of 1 for the running time, because all we want to do is to set a reference over here. That's all we got to do. And you want to watch out for the order of executing the statements of Java code, because the order does matter. You will see that the hints in the slides. What about the second method over here for insert before? Let's say this is our reference node over here. What I want to do is I want to insert some node before that, meaning that this is what I want to do, right? So let's say I'm going to create this node over here. Let's say I'm going to create this node. Okay, so this will be the new node I would like to insert before n, and then I'm going to have the elements and also the next. So the element here is actually going to point to wherever E is pointing to. That's the element, right? And what I want to do now is to make sure the next of the new node is pointing to n. That's what I'm inserting before. And what used to be pointing to n as its next, now it should be pointing to this particular new node over here, right? So you can imagine that there will be some node that happens just before, that actually that's situated just before n over here. So now would this be equally efficient to be done as the insert after? Will you be more expensive? It turns out this will be more expensive. It turns out it will be big O of n. So it's a linear time algorithm, right? It's definitely much more expensive than the insert after. Let me draw some analogy over here. You can think about this method over here is somehow similar, well, analogous to one method that we spoke about before, that we compare in just earlier part of the lecture. So this will be similar to the remove. Actually, that will be the add last. So that will be the add last. You can think about why. Versus this method here is analogous to remove last. Okay, remove last over here. You can think about why, right? I'll leave the analogy to you. Okay. Also, add last you happen to be constant time, and remove last happen to be linear time for very similar reason. Now, in this case, in order for me to insert this node before the reference node, I need to find out what's the node that happens before the reference node. In order for me to get to this node here, that will be the bottleneck, because I simply don't have the mechanism to really say, given the reference node, to go to its previous node, because I'm talking about singly linked node, not a doubly linked node, not, right? So this part here, let me highlight it to tell you that it is the bottleneck, right? So this one here is really the bottleneck, meaning that you have to use the get node add method. So this will be the performance bottleneck. Performance bottleneck in order to retrieve that particular node. Right, so that's about the visual hints I would like to give to you. You definitely want to understand conceptually why I'm trying to put these two methods side by side for you to really implement. But before that, you want to understand why. One will be constant time, similar to add last, and also the other one will be linear time, similar to remove last. All right, let me now go back to the slides, and then I'm not going to waste your time by reading off the slides, but you can simply just go over the steps hints over here I gave to you. I wrote it just in English. I think that that's pretty straightforward about what you should really do in order to implement. I'll leave the detail of Java code to you, right? But if you consider the written text over here together with the visual hints I gave to you, you should be able to implement the correct algorithm for these two methods over here. I'm going to leave them to you. All right, so one is constant time, the other one is linear time, as I explained. All right. So that's about the two exercises I would highly encourage you to really complete, so that you can basically I have assigned quite a good number of extra exercises to implement the basic operations that we didn't have time to really cover for the singly linked list. Complete them all. If you got any trouble understanding how to implement them, reach out to me. Right, the final thing I would like to talk about before that, so this will be just another method for you to implement, right? Is to implement a remove at, which will be very similar to add at. But now you want to know, if I really want to use the get node add method as a helper method, which node should I get to, right? So you want to think about it. So you may want to think about how we did the implementation for remove last. That might be something you want to think about before you actually, when you actually want to proceed with implementing this exercise over here. Finally, I would like to go over one table together with you to really compare the performances between arrays versus singly linked list. And later on, once we introduce the extension to singly linked list, which is called doubly linked list, we'll also compare all three of them again. But let's now do these two first, now that we actually already completed the discussion for a singly linked list. All right, let's now switch to iPad, right? And this might be a good time to have some pop quiz for you, right? To really see if you really have learned about the basic concept for singly linked list. Well, what I do is I got array, I got singly linked list over here, and I got different scenarios over here to really decide which the corresponding performance for choosing one data structure as opposed to the other, right? So this will be like a very important reference point for you as an engineer or as a programmer, as a software developer. Every time you want to decide which basic data structure to really use for your algorithm, you want to think about which of the basic operations are being exploited the most. In that case, you want to choose the most efficient data structure accordingly. That's what you got to do. All right. Let's now try to look at them. And I simply got the. You can see it's a very different way of representing or of storing data. Right? Remember, we talked about what the definition of data structure is. It's a systematic way for organizing data. This is how we organize a 3-name list, like a sequence. We got Alan, we got Mark, we got Tom, using a singly linked list. Versus if we simply got an array, it looks like an array is much simpler, but the flexibility and also the performance increase on certain scenario by the singly linked list is simply something that you cannot ignore. You definitely have to choose singly linked list in some scenario over arrays. All right, let's now go over the different scenario quickly. Okay, the first one over here. What about if you want to get a size of an array, or if you want to get the first or last element of an array, right? In the case of array, if you want to get a size, you simply say a.length, right? If you want to get the first or second element, you want to get its index 0, index 2, in that case, a.length minus 1, all of them will be array indexing, which is a primitive operation, constant time. What about singly linked list over here? Well, for singly linked list, don't forget we said we trade space for time. And for the singly linked list, we simply assume in the case of the singly linked list class, it's not really visualized completely over here, but just don't forget, we actually say we trade space for time, meaning that we got 3 attributes over here. So we got integer size. We also got the node for the head, and also we got a no reference for the tail. Right, so that's exactly the size, first and last element that we can get directly by returning the attribute values. Right, so all of them will be simply constant time. So that's why it's constant. Right, that one is straightforward. So if your algorithm is only about getting the size and also getting the first or last element, it doesn't really matter if you choose array or singly linked list because they're equally efficient. Let's talk about the next category. Let's say you want to get an element at index I, or if you want to remove the last elements. Let's talk about array first. Would then be expensive or cheap for the array? Well, think about how you can get an element at index I. What array indexing? Just A at index I. That cannot be simpler. What about removing the last element over here? So here I'm making some assumption over here. Let's say if I want to remove the last element from the array over here, in that case, all I can do is I can simply assign this reference over here just to be null. That would be effectively removing the last element without resizing. So that's the assumption I'm making, right? That's something I would like you to just keep in mind, the implicit assumption I'm making. For example, I can simply say, rather than pointing to the reference for Tom, it can be simply pointing to the null over here, right? So that'll be big of 1. So that'll be very cheap operations in the case of the array. Okay, so basically here I'm making the assumption that no resizing is needed. And what about these two operations for singly linked list, right? That's something we spoke about. Number 1, to get the element at index I. In that case, it could be the worst case, getting to the last elements. The last node in the list by starting from the head and then go all the way to that particular node. For example, the worst case would be the last node. What about removing the last element? Well, removing the last node. And in that case, we know from before that the bottleneck would be even though it's not exactly getting to the last node, but it will be getting to the second last node, right? That will be the bottleneck, right? So that's also something I want to highlight again. So this will be the bottleneck, the second last node. So this is the second last node, which is the bottleneck. The bottleneck for remove last, right? It's so important to understand this particular operation for syncly linked list. For both of them, it's going to be linear, as we explained before. You gotta use the get node at method as a helper method, right? And let's talk about the next category. Okay, let's talk about over here. Let's say if I want to add or remove the first element and last element, right? So let's talk about linked list in this case first. So if I want to add first, if I want to remove first, if I want to add last, we talk about all these methods already. All you got to do will be some setting some references, right? For example, if you want to add the last element, in that case, once you have created the new nodes, all you got to do is make sure the next over here is pointing to here, and the tail is actually reassigned to this particular node, and this node, the next will be just null, right? That's basically what we did earlier. So all of these will be cheap in the case of the syncly linked list, right? That one is actually pretty good for the syncly linked list. That will be just cheap. But before that, let me talk one more thing here. If I want to add or remove certain node or elements in the list, I'm talking about two different cases over here. Either the reference node was given, or if the node is not given. That will make a huge difference, right? If it is not given, that means you will need to call the add node at get node at helper method. In which case, the worst case, it would be linear time. But in the case where, for example, if I want to remove, let's say I want to remove maybe the node at index 4. In that case, if I can give you the reference to 4 minus 1, the third element's node, in that case, the reference will definitely help me to really not really having to call the get node at method to index I minus 1. I don't really need to, right? So that's why I'm distinguishing between the two, right? Let me now point it out over here, these two. Okay, so in this case over here, in the case of the syncly linked list over here, right, it's really important to see the difference between these two subcases. Either it is given or it is not given. In the case it is not given, of course, it would be expensive, right? You can see over here. In the case where it is given, in that case, you can there's no need to call get node at as a helper method. On the other hand, in this case, when the reference node is not given, in that case, you will have to traverse all the way to the node, the n-1 node, right? In that case, you will need to call get node at. So you really want to see the difference over here, all right? However, for all these operations over here, okay, so to either add or remove the first element, in which case I cannot simply just remove this element over here and assign that to null. In that case, I'm creating some null slot over here. Sometimes creating the null slot at the very end of the array might be okay, but creating that in the middle or at the very first element at the very first index over here will be problematic, because if people simply try to get to the 0 index or somewhere in the middle, somewhere except for the last one, if they try to get there, they might just get null pointer exception. So typically, it will be unacceptable to simply create some null slots somewhere except for the last position, right? That's something I'd like to mention. So if I for all these operations over here, it will involve some resizing of the array. And whenever you want to resize the array, you will definitely involve a loop to copy over all the existing contents, which we spoke about earlier, right? So that's why they will all be linear time over here. And of course, it will be important for you to notice that it's linear because they all involve some resizing of the array, right? And in terms of removing somewhere in the middle, it doesn't really matter if you are given the reference to the element or not, because you're still creating, you will still need to first of all creating some null slot over here and then shift everything to the left by one position, right? So for array, it doesn't really matter. But in the case of the linked list, if you're really given a node, for example, if I give you the node over here to say I want to remove this particular node, right? Well, let me say it again. Let's say I want to remove this particular node, and for your algorithm, I'm giving you the reference of the previous node. Think about this is at position I, and this is at position I minus 1. In order to remove the node at position I, I'm giving you the reference to the node at position I minus 1. In that case, I really don't have to traverse all the way to I minus 1. I don't have to. I can simply use it directly and set a reference from here to the node I's next, right? And then etc. Basically, right? So you really want to see why the difference will there will be such a difference between here linear constant time and also here linear time, right? Hopefully that's clear to you, right? You really want to study very carefully about this table here and also understand the assumptions that we're making, right? And that will really be a very good summary about what we have learned so far. All right, so this will be the end of what I would like to discuss about the singly linked list algorithmically. And the only missing piece of the puzzle before we actually talk about the doubly linked list extension, I would like to talk about how we can make the types of the elements in the singly linked list more flexible, but still consistent, but just a little bit more flexible. Let me tell you exactly what I meant very briefly, and then I'm going to talk about the details in the next part of the module. If you can just recall, the way we declare the classes for node and also singly linked list. Let me just bring you back to the earlier nodes over here. Okay, remember this is what we discussed earlier, and we talk about the singly linked list over here, and also the node class over here, and they are very specific about the type of element they store in the list or in the node. You can see here we got, let's say for the node class over here, we got the elements should be a string. Accordingly, whenever you want to create a new node, the element must be a string. And also, whenever you want to get the elements, the return value should be a string. And whenever you want to set the elements, the new value to be set should be a string. And that's about, right? But you can see everything is really about string, 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 and string. And similarly, whenever you want to declare the singly linked list class over here, you have to also restrict yourself into string only. For example, here you can see at the first elements, we have to give a string value. And if you want to add a particular index, it also has to be string, right? In some way, this is very simple, so we can actually focus more on the algorithmic parts for the singly linked list. But now that we understand the algorithmic part pretty well, I hope, so now we can actually now go on to improve the design for our two classes, for singly linked list class and also for the node class. And the improvement should really go as follows, briefly. We want to say whenever any user who want to use either this class or this class over here, they can somehow decide the type of element they would like to have. So rather than just having a singly linked list of singly linked list of strings, they might just want to have a singly linked list of integers, or maybe bank accounts, or maybe persons. So the type is completely up to the user rather than up to the programmer who actually has to program the algorithm for the node and for the singly linked list. Right? That's kind of the idea. And as for now, if I ask you to do the following task, rather than storing just string value over here for the node and accordingly the singly linked list, how can you make some extensions so that we can actually also have a linked list of integers? A very naive way to achieve this would be I can simply just duplicate another copy of the node class and duplicate another copy of the singly linked list class. Lots of duplicate. And the only change I will make on the duplicates will be I will change from string, 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 and also string and string over here. All instances of the string, I'll change them into maybe just integer. And that's the only thing I will change, whereas the rest will just be duplicates of code. And as you learned from the earlier Java courses, whenever you got lots of duplicates in your code, it's a no-no. It's definitely a bad sign about your design for sure. That's something we'll definitely like to improve by using so-called generics in Java. And I assume you already learned about the basics of generics maybe in the earlier OOP course, for example 2030, which is a prerequisite for the current course 2011. But anyway, for the next part of the lecture, I would like to I would like to present some reminders about how the generics in Java can be used, specifically for simply linked list and also for the node class, right? You would like to make sure you actually understand the background study that's required and also the reminders I'm going to present to you, right? Let me just go back over here, make a final annotation, and then we're done for this part. Okay, let me just go back to this diagram here. So we want to make it so flexible such that rather than storing just strings in the list, the user can specify, now I want to maybe only to store integers over here, maybe 23, 46, and 68 instead. Right? We want to remain the flexibility without having the need to really duplicate classes of nodes and simply linked list. We don't have to duplicate the code. So that'll be the idea. All right, so that's about what I want to say, just to give you some motivation to go on to the next part. And let's now move on to the next part to talk about generics in Java.